Back in the 1980s, Air New Zealand crew rosters were built by hand using coloured pencils and lines. They were very complex because they were complex rules for each individual pilot or cabin crew work group. First they developed sequences of work called crew tours of duty patterns, which covered the work the crew member had to do at the least cost. Then these tours of duty were built into rosters. Each roster was very complex and took at least 1 month to build. First they developed anonymous crew work patterns called tours of duty, which were sequences of work and rest periods that covered all of the airline's flights around the world. These tours of duty were then assigned to individual crew members to build a roster line of work for each crew member. Each roster was very complex and took 1 month to build. Then in 1984 we got together with David Ryan from the University of Auckland to start developing an automated system to build crew rosters.
Air New Zealand provided information about their tour of duty problem for a student project, and they liked the results so much that I took 6 months leave from the university to help them implement the system.
Each tour of duty starts and ends at a home base, and they have to comply with lots of rules for things like minimum rest periods and maximum amounts of time on duty, and they also have to take into account time zone changes. The rules are different for pilots and cabin crew and also for domestic and international flights. Each tour of duty contains one or more duty flights, and it can also contain passengering flights. This is where the crew member has to be moved from one airport to another as a passenger on the aircraft. This is a one-day national tour of duty for cabin crew. It leaves Christchurch for return flights to Auckland and Rotorua. This one is a 14-day tour of duty for pilots from 2000. It leaves Auckland for Los Angeles, Frankfurt and Papeete before returning to Auckland. PX indicates a passengering flight and a 0 indicates a rest day. Tours of duty have to provide the right number of crew to cover all of the flights on all the aircraft in the different fleets.
The tour of duty problems and the rostering problems are both very special forms of linear program. The variables of these linear programs can only take values of 0 or 1. For these optimization problems, each variable corresponds to one tour of duty, and each constraint corresponds to one of the flights in the flight schedule, and our objective is to minimize the total cost. Unlike linear programs that are considered at school, the linear programs that we solve involve hundreds or hundreds of thousands of variables.
Rostering optimizations can be much larger than tour of duty problems. The roster optimization has to include tours of duty, leave, training and on-call periods for either 2 or 4 weeks for over 2,000 crew members. The rostering optimization variables are all the legal combinations of tours of duty that will fit around each individual crew member's leave, training and on-call periods. The constraints make sure that each crew member has a legal roster, all of the flights have the correct number of crew members assigned, and also that crew members who speak multiple languages are assigned to the flights that need them. Lastly, the rosters have to meet crew criteria for quality.
David Ryan met with a number of pilots during the development to explain to them the optimization process. This was particularly important as many 767 pilots didn't think you could build a 767 roster with a computer. Pilots and cabin crew use different systems for organising their rosters. Pilots use a seniority preferential bidding system to express a preference for the kind of trips that they like to fly. It might be particular destinations, long trips, short trips, or grouping their days off. The optimization considers pilots in seniority order, so that a more senior pilot is more likely to get the kind of trips that he wants than a more junior pilot. The new system was much more flexible than the old system and considered many more possibilities. Pilots were much more likely to get a roster that they liked. Since it was introduced, we've changed the algorithm to reduce the bias given to seniority. Now, if 4 junior pilots can get a bid by denying a more senior pilot a bid, then the system will do that.
Cabin crew work patterns were distributed evenly across each crew member so that each crew member got access to the same sort of work over time. Between 1986 and 1999, 8 different optimisation-based systems were developed to cover all aspects of Air New Zealand crew scheduling. Tour of duty and rostering problems were solved separately for pilots, flight attendants and for flight engineers, both domestic and international, so there are 5 different crew groups with 2 different sets of problems. Air New Zealand was the first airline to use fully optimisation-based systems to develop tours of duty in 1986 and to develop rosters for international flight attendants in 1989. Research and development cost $2 million, but saved the airline more than $15 million. It also required fewer cabin crew members and pilots to operate the rosters, but equally importantly produced more quality rosters for both pilots and for flight attendants.
Each of the solutions to these problems came from an honours or a master's or a PhD project in the university, and many of these students went on to work at Air New Zealand. In 1997, 3 of the students who had worked on these projects for Air New Zealand formed a company which is now called the Optima Corporation. The Optima Corporation continues to provide support to Air New Zealand for the systems that we developed.
I started at Air New Zealand when we were going live with the first optimisation, and I worked there for 10 years. For my thesis, I wrote an optimisation for crew members on call. These crew members are called out if flights are disrupted or if other crew are sick. My optimisation works out which crew member to use out of all the crew who are on call. It also rebuilds the rest of their call period because different options are available after they've been called out. Once the optimisations were set up, 2 schedulers could build rosters in 4 days that had previously taken 6 schedulers 2 weeks to do. For the first time, we could use the optimisation systems to analyse hypothetical scenarios, such as setting up a cabin crew base for our long-haul crew in London, and this went ahead in 1999.
Before 1986, Air New Zealand had fixed rosters for 6 months periods of time. Now with these new systems, we can build crew rosters in 2 days and respond to competitive pressures and also changes in the market quickly.
Aircraft routes are usually fixed before the crew tours of duty are fixed, and that leaves fewer choices for the crew. What we would like to find out is how good the solutions will be if we solve the 2 problems together. Flight schedules are cheaper to operate if there are short turnarounds between the flights, but on the other hand, flights are often delayed because of bad weather or late passengers. If crew have to swap planes with short turnarounds, one flight that is delayed can cause a lot of delays in many other flights. In this example, the blue lines are the aircraft routes and the red lines represent crew if they swap aircraft. This sort of solution is not robust because one delayed flight causes many other flights to be delayed. We would like to find solutions that are robust, where crews stay with the same aircraft as much as possible, and if they have to change aircraft, they will get allowed as much time as possible for this swap. In order to obtain more robust solutions for the previous Air New Zealand summer schedule, we penalised crew if they were changing aircraft, and we were penalising them more the shorter the ground time. The minimal possible ground time for an aircraft swap is 30 minutes, which received the highest penalty. 35 minutes would receive less penalty, and if the crew changed aircraft with more than 60 minutes, they wouldn't get any penalty. The sum of all the penalties is what we call the non-robustness measure for the airline scheduling solution, and the lower this measure, the better. We integrated the aircraft routing and the crew tours of duty problems by going back and forth between the 2 problems iteratively, and in each iteration we increase the penalty for crew changing aircraft, and so that makes the solutions more and more robust. In this way, we got a whole series of solutions, and we stopped when we couldn't make them more robust. By integrating aircraft and crew, we were able to find much cheaper and much more robust scheduling solutions. The lower the dot, the more robust the solution is, and the closer to the left, the less it costs. Not many airlines have integrated aircraft and crew scheduling yet, so Air New Zealand could be among the first.